think about it for a second. How do you take the immense, concentrated weight of a skyscraper and transfer it safely to the Earth, especially when the ground itself is soft? Well, the answer lies in a really clever piece of engineering that's hidden right beneath our feet.
All right, so here's our game plan. First, we'll cover the basics. What in the world is a mat foundation? Then, we'll get into the nitty-gritty math that keeps it all stable. After that, we're going to walk through a real-world design example, run a super important safety check for something called punching shear, and then finally, see how it all comes together in the steel reinforcement plan. So let's meet the star of our show, the solution to that big question we just asked. It's a surprisingly elegant concept that solves the problem by spreading that massive load out as much as possible.
You know, the best way to think about it is like this. Instead of giving each column in a building its own little concrete shoe to stand on, you build one single giant concrete raft for the entire building to float on the soil. This is absolutely critical when the ground is weak. You see, individual footings would just sink into soft soil, kind of like high heels on a lawn. But a raft foundation spreads the weight out, just like wearing snowshoes lets you walk on top of deep snow.
And here, you can see exactly what that looks like in an engineering plan. All those squares you see, labeled C1, C2, and so on, those are the columns for the building. And notice, they don't have their own little footings. They're all resting on this one unified slab of concrete. That single base is the whole key to spreading that incredible load evenly across the ground.
But you can't just pour a huge slab of concrete and hope for the best. That would be a disaster. Engineers have to do some serious math to make sure the building's weight is perfectly balanced across it. So let's take a look at how they actually calculate that pressure on the soil.
Okay, now don't let this equation scare you. I know it looks a little intense, but it's really the heart and soul of mat foundation design. This is the formula that allows an engineer to calculate the pressure, that little Q, at any single point underneath the entire foundation. Let's break it down piece by piece.
So it basically breaks down into three main parts. That first bit, P over A, that's the simple part. It's just the total weight of the building divided by the area of the foundation. That gives you the average pressure. But the next two terms, well, that's where things get really interesting. They're all about balance. They calculate the effect of any tilting or bending that happens when loads aren't perfectly centered. Engineers call this turning force a moment, and you're about to see why it's so incredibly important.
And this right here is exactly why those moment calculations are so critical. Take a look at the diagram. See how the center of the load, the CL, isn't in the same spot as the geometric center of the foundation, the CG? That little offset, engineers call it eccentricity, creates a turning force. It's just like trying to carry a heavy box off center. It wants to twist right out of your hands, right? Well, that same exact twisting force is trying to tilt the entire foundation.
And that tilting action means the pressure on the soil below isn't nice and even. Instead, you get way more pressure on one side, that's Q max, and less on the other, Q min. It's just like when you lean to one side on your feet, you can feel more pressure on the outside of your shoe. The engineer's number one job is to make sure that maximum pressure, Q max, never ever exceeds what the soil can safely handle.
All right, theory's great, but let's see how this stuff actually gets applied in the real world. We're going to walk through a simplified design example to see how engineers analyze all the forces happening inside the foundation itself.
So to make these super complex calculations manageable, engineers have a neat trick. They imagine slicing the foundation into these long strips. And if you look at that top diagram, you can see what's going on. The big downward arrows are the heavy loads from the columns pushing down, and all the little upward arrows represent the soil pushing right back. It's like a constant battle between these two opposing forces. Now from those loads, they create what's called a shear force diagram. Now what's shear? Just think of it like a cutting force, like a pair of scissors. This diagram is basically a map that shows where those internal slicing forces are the strongest inside the concrete. We'll see in just a moment why those spots where the line crosses the center are so important.
And that brings us to the most important chart of them all, the bending moment diagram. If you take a ruler and push on both ends, it bends most in the middle, right? Well, this chart's peaks and valleys show us exactly where the foundation is trying to bend the most. And look at that. The highest value, 126.5, is right under a central column. This is the hot spot. This is what tells the engineers exactly where the foundation is under the most stress and where they need to add more strength.
Okay, so we've found our weak points. But hold on, before we can start adding reinforcement, there's one more absolutely critical safety check we have to perform. We have to make sure the columns don't just punch straight through the foundation. Yeah, it's called punching shear, and it's a very descriptive name. You have this immense concentrated load from a single column creating this high-stress zone right around its base. And the danger is that it could literally punch a hole clean through the concrete slab, which, well, that would be a catastrophic failure. And here's the thing. That risk isn't the same for every column. As you can see in these diagrams, an interior column has concrete on all four sides helping to resist that punching force. But a side column only has 3 sides helping out, and a corner column has just 2. This makes those edge and corner columns the most vulnerable spots, the ones that engineers have to check with extreme care.
So, we've analyzed all the forces, and we've checked for safety. The final step is to translate all of this complicated math into a physical design, the steel reinforcement that's actually going to give the concrete its strength.
And this is where it all comes together. See, concrete is fantastic at handling compression, being squeezed, but it's absolutely terrible at handling tension, being pulled apart. So remember that bending moment diagram, the one that showed us exactly where the slab was being stretched? Well, that's our treasure map. It tells us exactly where to add steel reinforcement bars, or rebar, which is incredibly strong in tension to counteract those forces.
And this is the end result. It's a detailed cross-section that becomes the blueprint for the construction crew. You can see it shows a grid of steel bars near the bottom of the slab to handle all that upward bending, and then another grid near the top to handle the tension right under the columns.
And these little notations you see, that's the language of construction. The symbol that looks like a circle with a line through it just means diameter. So when the blueprint says 020 at 10 centimeters, it's a very clear instruction to the crew on site. Take steel bars that are 20 millimeters thick and place them 10 centimeters apart from each other. All of that incredibly complex analysis gets distilled right down into these simple, precise commands.